Theorem 11 gives us some algebraic properties of the cross product. So if we let A, B, and C be three vectors in 3 space, and we're going to let C, without the bar over it, be a scalar. Okay. Property 1 says A crossed with B is the opposite of B crossed with A. The cross product is not commutative. This is what we call anti-commutative. Because not only is it not commutative, but there is still a pattern here. If I cross two vectors in the opposite order, I simply get the vector that points in the opposite direction. Now we sort of saw that when we talked about the right-hand rule. So if I have two vectors, purple and blue, if I cross purple, cross blue, I get a vector that's pointing upward. If I reverse that so that I cross blue, crossed purple, I'm going to get a vector that points downward instead. So I'm getting the opposite vector, it turns out, and we call that anti-commutative. If you remember, when we talked about why we have to state and sometimes prove that some of these algebraic properties hold, I said it's important that we don't make assumptions. We're calling this a cross product. That word product suggests multiplication, even though we're not calling this multiplication of vectors in 3 space. Seeing the word product, I associate that with multiplication, which I think of as being a commutative operation. So if I had just asked, is the cross product commutative? What's your gut tell you? Probably a lot of you would say, yeah, of course it is. And the answer is no, it's not. Okay. It's anti-commutative. If you reverse the order of the cross product, you reverse the direction of the result. All right, property 2 tells us how scalars interact with the cross product, and we had a very similar property for the dot product. If I have a scalar, this says I can scale either of the factors by that scalar and then work out the cross product, or I can just work out the cross product and then scale the result by that scalar. All of those things are equivalent. 3 and 4 are distributive properties. The cross product distributes over vector addition. But this is the first time we've had 2 distributive properties that worked with the same operations, just the cross product and vector addition. And the reason we need 2 of them is because we don't have a commutative property. If I have the commutative property and I said this worked, well, then I could switch the order of them and I'd know that worked too because it's the same thing. But since the cross product isn't commutative, we have to have basically both a left and right distributive property. So the cross product distributes with vector addition when vector addition is the right factor, and the cross product distributes over vector addition when vector addition is the left factor. Okay, properties 1 through 4 are fairly important to know because you might use those in your calculations. You might use them to take some shortcuts as you're calculating things. Property 5 deals with something called the scalar triple product, which we'll be taking a look at. We'll be taking a look at what the scalar triple product means in our next video. Notice this involves 3 vectors, and it's going to be a scalar because B cross C is a vector, but when I dot it with A, that's going to give me a number. Okay. Now, property 6 deals with the vector triple product. We're not going to be doing a whole lot of work with that, so I'm less concerned that you know this. It's true, it's stated, good to know, but not something that you need to worry about memorizing. The book's going to use this later on to prove Kepler's laws. I'm going to prove Kepler's laws as an optional topic a little bit later on in the semester. We don't have the tools for it yet. We've got to learn a little bit more before we've got the tools. I'll do that as an optional topic later on in the semester, but I'm going to use a different method than our textbook uses for proving it. I kind of like the method that the previous textbook that we used for that. Okay, so 1 through 4 are going to be fairly important because you might actually use these in your calculations. We're going to talk about 5 a little bit more in the next video, at least what the scalar triple product means. And 6, you can just consider sort of an interesting trivia fact. Now, of these properties can be proved by just breaking things into the component level. They're what I call sort of plug and chug proofs. You write down your vectors in terms of their components, and you just manipulate the symbols until you show that the left side of the equation is equal to the right side of the equation. Great exercises to do, but not particularly illuminating proofs, because I don't feel like when you've done that, you're left with any better sense of why it is that you're getting the results that you are. So I didn't assign any of these proofs. The book does prove, I think it proves question number 5, and then some of the others are properties in the, are assignments in the homework that I didn't assign. If you're interested in doing them, you're certainly more than welcome to, and I'm happy to provide you feedback on them. Okay, what I do want to take a look at is just our special unit vectors I, j, and k. Now, if I wanted to calculate I crossed with j, I certainly could do that very quickly just from the definition. I'm actually going to calculate it, though, by using our properties that we have of the cross product. So if I look at I crossed with j, I, remember, points straight out in the direction of the positive x-axis, and j points straight to the right in the direction of the positive y-axis. So I can figure out the direction of this by just using the right-hand rule. I'm going to take my right hand, I'm going to point my fingers in the direction of I, I'm going to curl them towards j, and my thumb points straight up. Now, because I knew that this cross product had to be mutually orthogonal to I and j, I knew there were two possibilities. It either pointed straight up or it pointed straight down. Those were the two possible directions. The right-hand rule tells me that it's going to point straight up. So it's going to be some positive multiple of k. But I can also say I know that the magnitude of I cross j is the magnitude of I times the magnitude of j times sine of pi over 2. Because I and j are perpendicular to them, so the angle between them is pi over 2. Now, I is a unit vector, j is a unit vector, and sine of pi over 2 is 1, so I cross j is going to be a unit vector. It's the unit vector that points straight up, so it's k. That's kind of neat, and it turns out if I cross any of these special unit vectors with any other one of them, I'm going to get either plus or minus the third one. And there's a nifty way for remembering that. If I just draw this little triangle here, and I draw in arrows going in alphabetical order. I points to j, j points to k, k points to I. If I go around in the order of the arrows, I crossed with j is k, j crossed with k is I, k crossed with I is j. If I go in the opposite direction, I want to remember that the cross product is anti-commutative, so j crossed with I is the opposite of k. I crossed with k is the opposite of j. K crossed with j is the opposite of I. Okay, that's just a neat way of remembering that, and that's kind of useful because we may be crossing these vectors fairly often, and it's kind of nice to know that. Okay. Want to just talk about one last property that we don't have. We've already discussed the fact that we don't have a commutative property. We do have a distributive property, which we're used to having. But the third property that we often have when we have multiplication is an associative property. And I want to just show you with an example that we don't have that. So the cross product is not associative. Let's just compare I crossed with I cross j and see that that's not the same as I crossed with I crossed with j. Now, using our little shortcut here for this cross product, I crossed with j is just k. So this becomes I cross k, and I crossed with k is the opposite of j. So that's what I get here. Now on this side, I crossed with I. So I've got a vector that's pointing straight out, and I'm crossing it with itself. Oh, these vectors, since they're exactly the same, they're parallel. They make an angle of 0. And remember, if two non-zero vectors are parallel, their cross product is 0. So on this side, I'm getting 0 crossed with j. And if I cross 0 with anything, I'm getting the 0 vector. So this example right here shows that it is not associative. Notice it only takes one example to prove that I don't have a property. If I want to prove that I do have a property, I have to work things out using arbitrary vectors that I write in terms of their components. But if I want to show I don't have a property, it just takes one example to say, nope, it's not going to be associative. So the cross product, even though we call it a product, is not commutative, it's anti-commutative, and it's not associative, and we don't even have any generalization of associativity that works. We just don't have an associative property.